Hello there, we're going to talk about mole today, and this is another important topic in stoichiometry. So look at this, if you ever air off, they have to go off and really quickly counter the force of a current in your body going forwards. So it has to be second. We're going to use that information, figuring out if we have enough large amount volume of gas in stoichiometry. So chemistry is used. So we're going to use something called the mole ratio today. And this is helping us in balanced chemical. We have to have a balanced chemical equation. And when we do, then we can use the numbers that we use for the balancing in something called mole ratio. So it's important. So we always have to balance everything first. We're able to use mole ratios to change from one thing to another in the whole balanced equation. So it will help us figure out how many moles we need of reactant to make a certain number of moles of product. So it's important. So mole ratios are the coefficients that are in front of a molecule or an atom in a balanced equation. So that's why we always have to balance first. And we can use this mole ratio as a conversion factor to go from a given moles to the moles that we care about. And we're also going to use this later on and start doing more complex problems. So this is a basic kind of ratio. And then we're going to build on this and have more and more different ratios, and we're going to use them in long strings of conversions. So instead of just having one step right here, we're going to start adding another step here and a step after that. So it's very important to know the mole ratio, and we always have to have our equation balanced first. So we have to have that skill under our belts. So the number of moles in a sample, we have to measure the mass, and then we use the molar mass to figure out the number of moles we have. So we'll do that a lot in lab, and that's a skill we'll use. So here's an example. How many moles of ammonia are produced when this many moles of nitrogen reacts with the hydrogen? So we're given this, we don't know this, and we're trying to go from nitrogen to ammonia. So let me go back. This was the equation we had in the last set of slides, and they should have written the equation here for you, but 1 mole of nitrogen combines with 3 moles of hydrogen to form 2 moles of ammonia from our last set of slides on stoichiometry. So it's a 1 to 3 to 2 ratio. So if I know this number for the moles of nitrogen that I'm starting with, then I can use the ratio of that to that and get to where I'm trying to get to. So I'm going to compare nitrogen moles to ammonia moles using the balanced equation. So the balanced equation is the recipe, and then we're going to say, hey, I don't have exactly what the recipe has. I have this much. How much can I make a product knowing I have this many moles of the nitrogen? How much ammonia can I make? So the balanced equation is your recipe, but sometimes you go in the kitchen and you don't have enough stuff, so you have to do like a half a recipe, or if you want to make a lot for a crowd, you double or triple the recipe. That's what we're talking about in these kind of math problems. So the ratio in the balanced equation is 2 moles of ammonia to 1 mole of nitrogen. If I didn't have a whole mole of nitrogen, I can start with I can change the recipe. I can change the like double or half the recipe. So this is kind of like I'm taking the recipe and cutting it in half. So I'm going to take 0.6 moles and wonder how much product I can make. So I know that this is what I'm given. This is all I have in the lab to use. I know that the ratio is 2 to 1. So these moles of nitrogen are going to cancel out, which I want. Then I'm going to take that number times that number, and it will give me the moles of ammonia that I can make in this recipe that I haven't changed the recipe, I've changed how much I can start with. Okay, so that's what this is kind of analogous to. So you could try that one. And these are more difficult problems. These are called mass-to-mass calculations, and we're going to need lots of steps in this. So we're actually going to put 3 conversion factors in a row. We're going to change mass to moles to a different thing that we care about, and then moles to grams. So they're showing it in 3 separate steps, but we can write it all out in a nice long string and figure it out. These are probably the more complex of all the stoichiometry problems. So let's use that same formula, same balanced equation, and we're going to start with 5.4 grams of the hydrogen. And then we're going to use all this balanced knowledge that we have here and figure out the grams of ammonia that we can make. Okay, so let's start with grams. Go to grams. We need 3 steps to get this to work. So we're going to start. This is important that you know this, so take your time on this. We're going to have the grams of hydrogen that was given. We're going to change it to moles of hydrogen using the molar mass. We're going to change it to moles of ammonia knowing the molar ratio. Then we're going to change it to moles of ammonia knowing the molar mass. Okay, so we're going to use given conversion factor, conversion factor, conversion factor. So here we go. This is our given. We know that for every 1 mole of hydrogen, it's 2 grams. We know the balance from the balanced equation what that mole ratio is. So we cancel that hydrogen. We're going to cancel out hydrogen, get to ammonia. And then last step is do the molar mass to get to the mass of ammonia. So this is really an important problem. I need you to understand it thoroughly and be able to do it on your own. So please try these types of problems. They're called gram-to-gram stoichiometry problems. So try some out of the book, anything you can find online. And I think I have one in the quiz coming up. So here's one you could try. And there's other stoichiometric calculations that we do, but I think the gram-to-gram is the most important for me. Also, easier ones, gram to mole, mole to gram types. So this is just telling you what we normally do in stoichiometry problems. Let's see if I want to talk about this. This is the same thing we were just talking about. We were going grams of something, one thing, going to grams of something else. Here's another way of showing the same thing we just talked about. So it's like a more general setup, but it's talking about the same type of problem we just did. So let's see. Let's talk about changing grams to molecules. That would be a good one too. So this one is going this many grams of water, and we want to know how many molecules of oxygen we can make out of this deal. So we're going to take 29.2 grams of water, we're going to run electricity through it, and we're going to make the 2 gases. We want to know how much of this we're going to make. So let's try this one. So here's our setup. This is our given. We're going to change grams to moles. We're going to change moles to moles of water to moles of O2, and then we're going to change it to molecules. So this is going to take a few steps here. So here's our given, 29.2 grams. There's 1 mole of water. This is molar mass, so it's 18 grams of 1 mole. It's a 1:2 ratio from the balanced equation. And last, so what we've canceled out is grams of water, moles of water, and now we're at moles of O2. And now our last step is they want a molecule, so we have to use Avogadro's number here. So this is another good problem to understand how to do. So please take your time and understand this one as well. Here's another practice problem for you to try. And then we can also do volume. If we're at STP, we can do that 22.4 liters. So this is saying they have 34 liters of oxygen, and they want to know how much nitrogen dioxide are produced. They're saying this guy is in excess. That means we have plenty of this. The thing that's limiting us is the O2. So here's all our given. Remember, 1 mole is always 22.4 liters at STP. So we were given the liters. We changed to moles using that 22.4 liter relationship. This is from the balanced equation, and then we're changing to liters, knowing again that 22.4 liters is 1 mole at STP. And so this is what we come up with. This is another good problem. And here's there's a problem you could try. I think I went too fast, sorry. Go backwards. Here's a problem you could try. And then here's another example of the kinds we were just talking about. So you can look through this one. This one's a little easier because we know we're at STP, we're at the same, we're at STP, so we can also just talk about these as molecules. And we can, we know the same volume of each gas has the same number of moles in it because of Avogadro's law, so that's what they're using here. Here's another one to try, and let's try a quiz. So you're going to have to get paper and pencil out. Good luck. Here we go. So how many moles of water are produced when you're starting out with 2.5 moles of oxygen? So pause me, use a mole ratio on this one, and see if you can figure it out. Okay, I'm going to go ahead and give you the answer. So see if you can get that one. If you didn't, figure out why. These are important. Here's another one. We have 3 liters of nitrogen, and we want to know what volume of ammonia is produced using the balanced equation. That equation, double check is balanced, and then pause me, do the math, come back, and I'll give you the answer. All right, here we go. That's what you should have gotten correct. Right, if not, double check yourself. Last question. We have the airbags, and it is this chemical reaction. And if we start with 5 grams of nitrogen gas, we need 5 grams of nitrogen gas. How many grams of the reactant? This is sodium azide. How much do we need to make 5 grams of gas? So pause me, try that math. It's going to be a gram to gram problem, so these are really important. This one you really need to know how to do. Pause me, and I'll do the answer in a sec. Alright, so you should get that as your answer. And so good luck with this section. It's very important that you know how to do stoichiometry. You'll use it throughout your science career. So stoichiometry is a really good skill to have. Alright, I'll talk to you soon. Have a wonderful day. Bye-bye.